Hello, and welcome to the flight readiness review for the INROS team for entry into Mach-23. The mission involves launching a rocket to 3 kilometers and delivering a payload. The payload involves investigating the feasibility of adhering solar panels to the external airframe to maintain vehicle health on the launch pad, as well as investigating the use of fixed flaps for descent control. You can see the team composition in the table. We wish to clarify if it's required for a faculty member to attend the event or not. So as mentioned, our vehicle Violin will deliver the payload to as close as 3 kilometers as possible before safely recovering itself using dual deployment. This will lead to a drift lower than 1.5 kilometers. You can see the success criteria outlined here. The only major change in CDR is cancelling the test launch due to time constraints in favour of validating all necessary subsystems / requirements individually, and this will be detailed later in the presentation.
Following deployment from the rocket, the main payload mission consists of 2 things. One is the characterization of the effectiveness of solar panels mounted on the rocket body as a way to keep the payload charged on the launch stand for future use where the wait time may exceed the battery life. The success of this can be verified by collecting stored data from the onboard power and current sensor. The second is testing the deployable flaps as means of increasing drag and providing safe recovery. The success of this can be checked by the physical deployment of the flaps at the given altitude, as well as data from the accelerometer. Then, defined by the requirements, the payload will collect and transmit GPS data back to the ground station for easy recovery, as well as the required altitude data and data storage.
The launch vehicle configuration remained unchanged since CDR, 3 body sections with motor and main parachute in the lower section, avionics bay in the center and payload together with a drogue parachute in the upper section. To ensure successful launch, motor mount features adjustable ballast rings and launch lugs are positioned either side of the center of gravity, one integrated with the fin cam, another rail button at the top, and both are designed to withstand twice the expected maximum loads. The glass fiber reinforced body tube has been designed and tested to ensure excellent radio transparency to aid with recovery and launch status visibility. The structural integrity has been ensured by accounting for the worst case thrust force and deployment shock loss propagation. The eye bolts have been mounted onto the motor case, either side of the avionics bay section, and to the nose cone. All closed chambers include vent holes, and to improve the final assembly operations, both avionics and the payload sections have been designed with smooth and repeatable integration in mind. Current system launch mass has been estimated at 11.89 kilograms, with the landing mass approximately 3 kilograms lower. The design features 322 components in total and 100 unique components, though electrical circuits have been classed as a single component. The great majority of these would be pre-assembled prior to launch. The majority of launch vehicle airframe components have been manufactured either by the team in-house or by the external suppliers. The next slides will describe these in more detail. Subsystems integration stage is currently ongoing for planned system assembly and integration prior to the launch event. This is to ensure minimum construction is to be completed on-site and will only include parachutes packing, black powder filling, motor integration, and final vehicle assembly. More information will be provided later in the presentation.
Each fin has 4 channels designed with a teardrop cross-section to ensure no support structures are required in the 3D print process. These channels are 2 mm wide and 90 mm deep, and will have a steel rod of the same dimensions inserted inside in order to support the fins during lateral loading to minimize deflection. A section of the external blended surface has been removed to allow for the launch rail to be unimpeded during launch, and 3 launch lugs are included in the can design, which will be tested to ensure they can withstand launch loads.
The 20 mm thick ballast ring provides a majority of the mass, with the 3 mm and 1 mm rings intended for finer mass control.
The final on-site assembly will involve assembling the avionics stack, which can be seen partially assembled with and without the avionics airframe tube on the right, connecting the batteries, switches and E-matches using the screw connectors on the avionics boards. And the final avionics sets pre-launch will be closing the screw switches to power the circuit, performing a final communication check to ensure the vehicle and payload data is being correctly received, and finally removing the remove before launch pin, enabling the pyrotechnic channels.
At the apogee, the first stage of the recovery system will take place with deployment of a 12-inch parachute to begin descent. The parachute will provide enough drag to decelerate the payload to roughly 15 meters per second, which will be maintained until the payload has reached an altitude of around 200 meters. At this altitude, the ET quark will put a current through the macron wire, releasing the 4 flaps simultaneously along with a strong fabric connected between each flap to increase frontal area, which is the second stage. These flaps will further decelerate the payload to around 5 meters per second for a safe landing.
The design is constructed of 3 aluminium bulkheads shown on the slide, along with an inner casing and outer tube that will flap up to form a drag system as part of the recovery system. The upper bulkhead was designed with 4 flat surfaces allowing for the attachment of the spring hinges, along with 3D printed adapters that fit flush with the curved surface of the flaps. This aspect of the payload will allow for the flaps to deploy as discussed previously. The outer flaps of the payload have been adapted with holes down the vertical edges of each flap to allow for attachment of fabric, which will deploy with the flaps, and 2 holes at the bottom of each flap for the 2 sets of fishing wire to be securely connected to each flap, one which will burn to release the flaps, and the others to hold the flaps at 90 degrees to the CANSAT body, preventing over-rotation. This will all be held together by rods running the length of the CANSAT. Sliders have also been 3D printed, which slide onto the rods for mounting the payload avionics.
The battery should last for about 3 hours. Payload electronics are connected to the solar panels mounted on the airframe of the rocket via magnetic connectors, with current and voltage sensors connected to the solar panels. This is a test to determine the viability of using solar panels to charge the payload battery when the rocket is on the stand for longer periods of time. That being said, for the launch at Mach-23, the battery selected is rated to power systems for the duration of the mission without the need to charge. As the COTS computer used for flaps deployment is powered separately due to a significant power draw, the total power draw was calculated at 783 milliwatts, and since a 3.7 volt battery is being used, this requires a 211 milliamp 3.7 volt current draw. Adding a 3-hour runtime and a safety factor of 2, a 1.8 amp hour battery is required, and so a 1.8 amp hour LiPo battery was chosen, with a nominal current draw of 340 milliamps. For ease of use and safety, a screw switch will be used to turn on power to the payload prior to launch. Step-up and step-down voltage regulators are included in the final circuit as different components have different voltage requirements as shown. The payload also includes an altimeter, accelerometer, and a GPS module, which will send live telemetry to the ground station and provide a location after landing for recovery. Assembly of the payload, including electronics, will happen before the day for the most part, as the CANSAT can be transported assembled. The only steps that will need to be taken on site before launch is the connection of the magnetic connectors to the airframe-mounted solar panels, as well as using the screw switch to turn on the avionics in the payload.
Pyrotechnic charges will be used to deploy the drogue, payload, and main chute. We utilise a 96-inch main as well as a 12-inch drogue, and the main parachute, the drogue parachute will deploy at apogee in the main parachute at about 500 meters. We were concerned about the shock loads induced when the main parachute opens, so we've made extra effort to ensure this is not an issue. This involved ensuring all parachute rigging attachment points are designed robustly. Additionally, we've completed analysis on the cords used and figured out what shock loads that's going to develop. We've tested the avionics bay, which does not yield, the avionics bay, which is the weaker part, which doesn't yield into about 4.5 kilonewtons. Regarding deployment, we will use the 8-timer Proton as our main computer, as well as the 8-timer Quad as a redundant computer. Each one will be connected to isolated pyros as shown in the figure, but we're still deciding whether to have 2 separate charge bays, each with the required amount of black powder, or having them all combined into one. We'd like to hear your advice on this, as there are pros and cons to each.
The avionics bulkheads must be able to survive expected parachute shock loads. We were able to calculate a range of values from 3,000 newtons up to 7,000 newtons at the max. In order to verify our design, we've been able to make test bulkheads with 1000 series aluminum alloy. Running FEA simulations, we were able to obtain max deflection of about 0.1 millimeters occurring at the center of the port and max stresses occurring at the M4 steel rod fixtures. To validate our results and accurately simulate the recovery process, we conducted tensile tests on the full body tube assembly. At 3000 newtons, we were able to get deflection values of 0.1 millimeters per bulkhead, which is reflective to the values obtained during FEA simulations. Running the test again at 4500 newtons, yielding started to occur, and we obtained deflection values of up to 2 millimeters. Upon closer examination, it was determined that the extension was caused by the quick links yielding rather than any damage to the bulkhead itself. The bulkhead that we will use for launch can now be seen on the screen and is made of 7000 series aluminum alloy, which has a yield strength 17 times of that of the 1000 series we previously tested.
As mentioned, the body tube is made of glass fiber reinforced polymer to a bespoke design due to an optimum range of properties for our application and is currently being manufactured by Collins Aerospace. Test body tube has been manufactured and tested in compression at 1500 newtons. Since the test article survived the given load case, the actual flight body tube is validated by similarity and analysis. The test tube is representative of a flight body tube, and the load distribution calculated across the body tube length should not exceed the tested scenario. The axial and hoop strength of the flight body tube has been further increased by increasing the outer diameter and tailoring the fiber layup for backlink loads.
The material properties applied to the fin can and nose cone in the following simulations is not fully representative of the material properties of the final product, as AMCO, the company we're outsourcing the manufacturing to, have altered their print resins to improve the yield stress and ultimate tensile strength of the material as per our requirements. However, they haven't provided these improved properties to us. This means that the safety factors and deformations shown should improve in the physical testing. The load case applied here was the weight of the launch vehicle laterally to the fin tip, which is 110.52 newtons, and this resulted in a maximum displacement of 16.1 millimeters, which is within the required maximum deflection of 16.48 millimeters as per the requirements, with a minimum safety factor of 1.89. This is the result from the longitudinal loading. The load case was twice the maximum acceleration of the rocket multiplied by the mass of a single fin, resulting in 11 newtons of force. This resulted in a maximum displacement of 0.18 millimeters and a minimum safety factor of 170. These FEA simulations will be validated through physical testing. The launch lugs have been tested to ensure they will be able to withstand launch loads both longitudinally and laterally. The load cases applied in both cases is 200 newtons, which is roughly twice the rate of the rocket, in order to introduce extra factors of safety in the case of a shock load being applied to the lugs during launch. The lateral loading resulted in a maximum displacement of 0.08 millimeters and minimum safety factor of 5.51. Here you can see the longitudinal load case, which resulted in a displacement of 0.04 millimeters and a minimum safety factor of 9.88. And these two FEA tests show that the launch lugs are structurally able to withstand the launch loads applied to them, and this will be validated through physical tests as well. Here you can see the nose cone FEA testing results. The loads applied were 20 Gs of acceleration to simulate the launch acceleration of the vehicle, and 650 newtons applied to the skin to simulate the drag force experienced at max Q. These load cases resulted in a maximum displacement of 0.321 millimeters and a minimum factor of safety of 5.15.
Multiple methods have been investigated to determine the expected shock loads during parachute deployment. As the limiting load case, the main parachute deployment sequence has been used. The final method selected uses the equation of motion evaluated implicitly over time, taking into account the change in mass and parachute drag. The team has performed tensile tests, as shown on the slide, of bungee cords, harness, and also structures to obtain max loads and stiffness characteristics. The team is further planning to perform a parachute deployment test to capture filling time and correlate it with analysis to validate the lower 3000 limit loads as expected when parachute reefing is applied.
Two finite element analyses were conducted on the piston heads in the deployment system. The first case was to simulate the thrust loads at peak thrusts of 20 G acceleration and 1600 newtons. The second case was to simulate the deployment of the piston heads, or the deployment of the payloads. This was 1000 newtons. The minimum safety factor was 9.93 for both simulations, and a maximum displacement of 0.026 millimeters.
To test the vehicle data transmission, the avionics was set up with all the structures and tested to a range of 800 meters with full communication and all the packets properly received. The preamble and setup bits have also been changed, which should prevent interference with 868 MHz systems of the other teams. The 2.4 GHz payload doesn't need to be concerned with this interference because of the built-in frequency hopping spread spectrum.
In line with the Mach-23 guidelines, the payload employs a recovery system that keeps it at an acceptable calculated landing speed and within the maximum drift distance of 1.5 kilometers, as discussed in the final design overview. All calculations related to structures and electronics have been done with a safety factor. The components that have been implemented in the payload avionics allow for the required GPS and altitude measurements, as well as data storage using a microSD. At this stage, the structure is in the process of assembly and further testing to ensure functionality and durability of the flaps and recovery system. These tests include a wind tunnel test for flaps deployment, as well as a full payload drop test. The avionics is currently in the middle of breadboarding, with individual sensor tests completed, as well as multiple sensor tests, both of which have been successful and provided the expected data output. Following this, the plan is to test the data storage function and build the power system to test and then integrate. Final tests will be performed to check the function of the system as a whole. And this test procedure has been employed to ensure that issues with the system in a less complex state are spotted and fixed before finalization and launch.
Overall, team confidence in the system, from the ground station to the launch vehicle and the payload, is high. The testing plan is being carried out and regularly updated. Key tests yet to be completed are the black powder deployment tests at Midlands Rocketry Club on the 17th of June, payload wind tunnel flap deployment tests on the 24th of May, payload drop test on the 29th of May, and parachute deployment tests on the 19th of May. In order to verify our design, we have a rigorous testing plan in place. We have 44 tests in total, 16 completed, 8 in progress, and 20 planned. We will now briefly cover our progress through our testing plan. The avionics tests are mostly complete, with development of the ground station app in progress, and therefore it is yet to be fully tested. The airframe requirements are mostly verified, having used the test article of the tubes to verify tensile and compressive load cases. The fin can has also been tested using a prototype and finite element analysis software. The propulsion and flight requirements are partly verified, with key remaining tests being black powder deployment testing to occur at Midlands Rocketry Club in June. The payload electronics testing is mostly complete, verifying key requirements. Structural requirements are not yet fulfilled, as manufacturers slipped, though we are close to finishing a test article and have tests planned as shown here.
The launch procedure is outlined in the table. This is quite dependent on weather conditions, so we've accounted for the possibility of assembling the vehicle one day and then launching the next, but also if required, the T-1 day activities can be done on the day of the launch. We estimate that from arrival at hangar to being ready to launch can take about 2 to 3 hours, assuming that no issues occur, and we will do a dress rehearsal of this before the event to provide you with a more accurate estimate. However, we cannot do a full system test integration before the event as we do not have the motor grains, so this poses some risk to the on-the-day assembly. Each of these steps has launch operation procedure, documentation, attached in appendix. All data after the launch should be collected on the ground station for easy processing, but in case of issues we should be able to recover it off SD cards and quickly process it for the post-flight review. Obviously we are not in the flight ready state as of today, however we are not concerned about the remaining work. The airframe tubes will arrive by the 29th of this month and we've lined up all the remaining manufacture to be ready for this point for a full system assembly soon after. This should allow us time to identify any issues and correct them in the remaining month. The remaining AIT will be adhering the solar panels to the outside of the airframe, but this should not affect full system assembly. And the final bit of validation takes place at MRC in June, which is where we test the recovery system pyrotechnics for the deployments. We just wanted to clarify, we have the motor hardware as shown here. Am I right in saying that all the other required parts, so the motor grains, the O-rings, igniters, etc., will all come with the grain set, which is being shipped directly from rockets and things to the launch site?
The main outreach being completed alongside the mission is the project with Ivanhoe School in collaboration with Not Space, where they have been developing a second set of avionics to be integrated into the team payload structure, with the main function being data collection on gas composition and the presence of any pollutants in the area. Outreach work has also been run alongside the project, with members attending a Girls in STEM Day with Welbeck Primary School to teach the kids about space and help them build launchable paper rockets.
So in conclusion, we have progressed greatly with the assembly, integration and testing of Violin since the CDR, and we are close to having the full system ready, and we are confident that the plans outlined for the remaining work will ensure the team's readiness for the event. And we'd like to thank Chantal Capoletti, Jess Turner, Steve Creedy, Andrew Hallam, Thomas Haskins and the L2 technician team for supporting us through the manufacture, as well as AMCOE, Collins Aerospace and RS Grassroots for sponsoring the project.